Well, we've finally come to the substitution method. So this is going to open up a whole bunch of functions we will be able to find the antiderivative for. Basically, the substitution method in one sense is undoing the chain rule. If you remember the chain rule from differentiation, the derivative of a composition. Remember, this is f, capital F of little g of x. This is not capital F times g of x. So you're not multiplying these functions together. Remember, what you're doing is you're taking x, plugging it into the function g, getting the output, and then plugging that into the capital F function. We say that's a composition of f with g. So remember, the chain rule says the derivative of such a composition function is the derivative of capital F. Now, capital F we sometimes call the outer function, and little g the inner function. And so this is the derivative of the outer function, capital F, evaluated at the inner function g, and that little dot means multiplication, times the derivative of the inner function. So that's the chain rule. I hope you remember that from Calculus 1. But the minute, excuse me, the minute I have a derivative, right, I also have an integral. In other words, this function here, right, if I were to integrate this function, my question would be, what's the antiderivative? Well, I know what function I took the derivative to get this. It's what's inside here, right? So the integral of this gives us back to what we started with, of course, plus c, right, plus the arbitrary constant. So you can see how this is really going to be an undoing, if you will, of the chain rule. Okay, we want to clean this up a little bit. So notice if I let capital F prime be little f, so that capital F is the antiderivative of little f, right? So I'm just going to do this for a change of notation. Then we'll have f prime is little f of g of x times g prime of x, and that's going to be equal to capital F of g of x. So remember, little f now is our outer function. Inner function is g of x. And notice we have times the derivative of the inner function. This is the form that we will mostly use the substitution method for, and it's where we're going to start out with. And so with that form, we know what the antiderivative is. It's just what? Take the antiderivative of this outer function, right, and plug in the inner function. And that's it. Typically, the way this is expressed is a little bit cleaner. If I let u, the variable u, represent the output to the function g of x, so u is g of x, then with the Leibniz notation, du dx, this is the derivative of u with respect to x, is just g prime of x, right? Or in terms of a differential, if I multiply both sides by dx, du is equal to g prime x dx. And this is Leibniz notation, very helpful to understand the du and the dx. This will become important if you've been doing your integrals without the little dx right at the end, sort of skipping that. You're not going to be able to do that here. It's because it's important. It's related. These different variables, if you will, u and x, are related differently. So substituting this in, right, u is g of x, so that's f of u, and then g prime of x dx, right, g prime of x dx is just du. So this is the way it's usually written, and then it's what? Equal to capital F, g of x being u, capital F of u plus a constant. This is the way it's typically expressed, okay? And in fact, because we use the letter u by convention, it's sometimes referred to as u substitution. The letter u is used a lot with substitution, but sometimes we use other letters as well. And of course, it depends on the original integral, what variable of integration we have there. So just a review about these du and dx's. If you didn't do this in Calc 1, these are called differentials, and they're very useful. It's one of the greatest contributions that Leibniz, who was one of the founders of calculus, if you remember, him and Isaac Newton sort of were the founders, in quotes, of calculus. A lot of work had been done prior to them, but sort of independently they understand the relationship, basically the fundamental theorem of calculus and other things that we've talked about. Newton's notation, though, isn't really used as much as Leibniz notations is, and so we make use of his differentials. And so we're going to treat the differentiables like they are variables, and that will greatly simplify this process. Okay, and so let's look at the substitution method. It is, as it says, a bit of an art, but for the ones we're going to see, the key is to find the inner function and let that be your u. In this case, I'm going to let the letter u. First several examples, we give you the u. So here I'm looking at the integral of 2x times the square root of x squared plus 3. Notice I couldn't normally just find the antiderivative. Remember, you can't find the antiderivative of 2x and then the antiderivative of this somehow and multiply the two together. That's not going to work. I can't distribute the 2x inside the square root, right? I can't do that. And so we're really kind of at a loss. But notice I've got the x squared plus 3 function inside what? The squaring function. There's a composition. And notice further that the derivative of the inner function x squared plus 3 is 2x. And so I'm multiplying, right, this idea of multiplying the derivative of the inner function times the f of the inner function. All right, if it's in that form, I'm going to be able to do it by letting u be this inner function. If u is that inner function, things are going to clean up. And this is the way we usually do it. We'll start with this u, and then I'll just say, this first time I'm going to say du over dx. What's the derivative of u with respect to x? What's the derivative of x squared plus 3? Oh, that's easy. That's just 2x, right? And then what I like to do is write it in differential form. In other words, I'm going to treat, even though du dx really is one thing, I'm going to treat du as a differential of u and dx is differential of x, and treat these as separate variables in a sense, even though their quantities we're not going to come into play when we're calculating the derivative, but we get this relationship that du is, sorry, when calculating the integral, 2x dx, right? Multiplying, if you will, both sides by dx. And so this is the way we play around with differentials, and it's helpful from what Leibniz has done. So what I'm going to do is I'm going to substitute everything from x, right, to u. Everything has to be now in terms of u. And so let's do that. First of all, let's take a look at the square root of x squared plus 3. What does that become? Let's do this in green. The square root of x plus 3 becomes, well, x squared plus 3 is just u. This becomes the square root of u. Okay, so that takes care of that part. What about what's left? Times what? 2x, and don't forget our dx, right? The 2x times dx. Well, what's 2x times dx? That's just du. So that's going to allow me to just put in that du. So everything, including the dx, gets converted to u variables. There should be no x's at all here. Okay, and now this integral is something we can do, right? This integral is fairly easy to do. Notice this is really the integral of what? Square root of u is u to the 1/2 du, and I can do that. That's just simple power rule. And part of the process of substitution is to make the integral easier to do. It should be easier to do, something we can do. Okay, if the substitution doesn't give us something we can do, then it's not going to be very helpful. So what's the antiderivative by the power rule? I add 1 to the half, I get u to the 3/2 power. Divided by 3/2 is the same as multiplying by 2/3 plus a constant. So there's the antiderivative of this, but remember we want the antiderivative of this function in terms of x. How do I get that? Well, I just replace u now. You go back to the original variable and replace u with x squared plus 3. So my answer is 2/3 u, which I need to put in parentheses, right, x squared plus 3 to the 3/2 power plus our constant c. And that is the antiderivative. And you could check, you could take the derivative of this, right, and you'll get back to what we have here. You should check and confirm that. And you can see in taking the derivative of this function here, we're going to be using the chain rule, and it should make sense because we're undoing the chain rule. Okay, let's do a few more. Here we have the integral of 35 cosine of 5 theta d theta. Now we looked at this one before and have already talked about cosine of 5 theta, if you remember, but now we can formally do it with substitution. This is cosine of 5 theta, not times 5 theta. I can't factor this 5 out. It's 5 theta inside the cosine function. So I'm going to let u be the inner function, 5 theta. And what's du? What's du? Well, du d theta, notice our independent variable instead of being x is theta here, is 5 and I'll just do d theta. Okay, so it's du d theta is 5, then multiply both sides by d theta. And this is the way I'll usually write this from now on. When I take the derivative, I will put the du and the d theta. That's going to be part of the process. All right, and so with that, we can now transform this. All right, and the thing is, there's a couple ways of doing this. I've got a 35 d theta. Okay, and here I've got a 5 d theta. What I like to do is balance this equation out so it matches what I have here. Okay, there's other ways of doing it. This 35 is a constant multiple. You can pull it out and you'll just be left with d theta, or you can obviously pull out what, 7, and you're left with 5 d theta, and now you're set to go. But I just like to go and do what? Go ahead and take care of it here. Multiply both sides by 7. So 7 times du, if I multiply this side by 7, is 7 times 5, 35 d theta. And now I've got it covered, right? 35 d theta is 7 du. So what does this integral become? It becomes the integral of cosine 5 theta. What's 5 theta? That's u. Cosine u times 35 d theta. 35 d theta is 7 du. Now this 7 again can come out because it's a constant multiple. So this is 7 times the integral of cosine u du. So if you went ahead and factored out a 7 out of 35 and be left with 5 d theta, you would go right to here. That's fine. I mean, it's the same thing. Okay, I like to do it this way better. It gets a little confusing about you're not quite sure what do I need to factor out of here. And so, there's multiple ways of doing it. I like to do it this way. But now the important thing is I can do this integral, right? What's the antiderivative of cosine theta? This 7 is a constant multiple pulled out. Antiderivative of cosine theta is sine. Cosine u, rather, is sine u. Because notice we're in the u variable. But we do want to go back to theta to get the answer, of course. U is equal to 5 theta. And so my final result is 7 times sine of 5 theta plus a constant. Okay, let's do a couple more. Okay, so here we've got negative 6t squared times e to the negative t cubed. So notice the outer function, we have a composition right here. The outer function is e to the u, where the inner function u is negative t cubed. So that's why I'm letting u be negative t cubed. All right. So notice if u is equal to negative t cubed, let's take the derivative. Du would be what? The derivative of negative t cubed is negative 3 t squared, and then dt, right? So du dt is negative 3t squared. So du is negative 3 t squared. Now I look over here and I've got a negative 6t squared dt. Looking at that part of it. And so what do I need to do to get negative 6? Multiply both sides of this by what? 2. So 2 du is 2 times negative 3, negative 6 t squared dt. So now I can change everything over. This integral becomes e to the negative t cubed. E to what? The u times what? Negative 6t squared dt is my 2 du. Again, I can pull that 2 as a constant multiple outside the integral, and we've got this very simple e to the u integral, which is the simplest antiderivative, right? The antiderivative of e to the u is e to the u, right? Don't forget our plus c. But last but not least, we're going to go back to the original variable t and replace u with negative t cubed. Again, you can check by taking the derivative of this function using the chain rule and observe that you indeed get back to the original integrand, the original function you're integrating. Okay. Let's take a look at this one. Here we give you the u, and you might be thinking, where's the composition? I just have one polynomial divided by another polynomial. And we chose u to be what? Looks like the bottom, the denominator polynomial. Why did we do that? Well, really, I'm thinking of what? 1 over u as the outer function and replacing the inner function then with this. So why 1 over u? Well, what's the antiderivative of 1 over u du? That's the natural log of the absolute value of u, right? Natural log integral. And so that's the form we see it in. And so notice when I have u being this, my du, the derivative of this is going to be what? Bring the 3 down, 6x squared minus 7, derivative of 7x, and derivative of 10 is 0. And notice that's exactly what we have up top. And so it's this, right, dx, right? Du dx is 6x squared minus 7, so du is 6x squared minus 7 dx. And that's 6x squared minus 7 dx. That's exactly what we have there. And so this becomes just the integral. Up top, 6x squared minus 7 times dx. That's just du up top. On the bottom is what? 2x squared minus 7x plus 10. That's just u. It's 1 over u du, or du over u, which is the natural log absolute value of u. Don't forget its absolute value of u, and then don't forget our plus c. And there it is, right? It's a simple integral. Replace now u with this expression, and we get the answer that we want in terms of x. X cubed minus 7x plus 10 plus a constant. Okay. And again, take the derivative of this, and we can check and verify that that indeed is the original function. Okay, so up to this point, we've given you the u. From now on, we're going to not give you the u, and we've got to figure out what it is to proceed. But you can see it's the inner function of the composition is typically what we choose u to be. There are some exceptions to that later on, but right now that's where we're going to be. So it's really a fun method. It's a powerful method, but it's really fun. And I hope it's kind of like unraveling a little puzzle, trying to undo the chain rule, find that inner function, and then get everything to balance out, by multiplying these little differential statements to get everything to work out. And of course, make sure every variable is turned over to your new variable. We've been using u every time. You don't have to use the letter u. It could be, I could have used t down here. Anything other than x would be a valid way to do it. But we used u a lot, and again, sometimes it's called u substitution, but this is the method, and so we'll look at some more examples next.